Good evening. Good evening, everybody. Thank you so much for joining us tonight for Brews and Breakthroughs. My name is Ellie Hayes, and I am the Executive Director for Missouri Cures. And we are a nonprofit organization that works to promote and protect medical research in the state. Just this past year, we've seen some attacks on medical research across the country. In Idaho, there was a law introduced that would make it a crime to administer an mRNA vaccine. There have also been similar bills floated in both North Dakota and in Florida, so we're keeping an eye out for that. Here in Missouri this year, we saw House Bill 1169, which would have established a different definition for the processes for medical research and food production than the national standard. For example, this bill would have established Missouri researchers and food producers differently and defined differently what constitutes gene therapy and how our food is labeled. So we were part of the coalition that helped to speak up and speak out. Some of the volunteers here called their legislators. We appreciate it. Thank you so much. To let them know that we want a fair playing field with everybody else in the country. That's the kind of work that we do at Missouri Cures. We try to make sure that any research that's legal at the federal level remains legal here in our state of Missouri. And then we promote the incredible work that's happening all across the state. Here in St. Louis, of course, we have Washington University, who's doing some incredible work. And our researcher here, Dr. Jason Weber, is from there. But we also have St. Louis University. In the middle of the state, of course, we have University of Missouri-Columbia. We have Stowers Institute in Kansas City, the Children's Research, Mercy Children's Research Institute in Kansas City. So there's research happening all across the state. And so we're the organization that promotes their work and then also makes sure that the work that they're doing is protected in our state. So that is the work that Missouri Cures does. So I would, if you haven't already, invite you to become a member of our Advocate Alliance and help us to protect medical research in the state. If you're a young person, we have a Young Friends group. You can find all of this information on missouricures.org. Our Young Friends group is going to be hosting a really cool movie viewing later in the fall. So keep an eye out for that. We have another Brews and Breakthroughs coming up in Columbia. Keep an eye out for that. And then we also will have a rare disease forum coming this fall. So we're really excited about all of our events. Without further ado, I'd like to introduce you to Dr. Jason Weber. He has been here in St. Louis at Washington University School of Medicine since 2001 when we stole him away from St. Jude's. Thank you, Dr. Weber. He is a professor in the Department of Medicine, Oncology, the Oncology Division, Molecular Biology, Molecular Oncology, Department of Cell Biology and Physiology and Biology. And he's going to talk to us today about his emerging research and breast cancer research. Thank you.
Well, good evening, everybody. Thank you, Ellie, for having me here tonight, and thank you all for coming. Just a quick shout out. Some of my lab is over there, so feel free to hit them up in between drinks for any questions you might have. They're really on the ball now and will be even more so later. They never pass up a chance for food and drinks. So I'm kind of going to walk you through sort of my own journey and then get you into what the lab does and what's going on here in your own backyard. And I think one of the things that's important, I do a lot of events like this to get out in the public to sort of disseminate all the things that are going on in St. Louis and WashU. And Steve, I'm going to kill you because I'm a mover. I don't like to just stand around. And then kind of sort of make you aware of what's going on, because a lot of times people don't realize the things that are going on in St. Louis at the level of biomedical research and treatments. So like Ellie said, I'm at WashU. I have been since 2001. Before that, I was on at St. Jude working on pediatric cancers. It was really easy to come back up here. I'm a native. I grew up in Edwardsville. And so, you know, it was really fun to get recruited to come back here and run now the breast cancer program for the Siteman Cancer Center. And now I do a lot with mentoring students I teach graduate students, undergraduate students at the Danforth, medical students. And it's really sort of this holistic picture, if you will, of what's going on at WashU, all the way from education to what's going on in the labs and then what's going on in the clinics. So I want to give you a good sort of picture of how that's working. So when I got into science, as an undergrad, I went to Bradley University in Peoria, Illinois. Did not know the joke of if it doesn't play in Peoria, it's not going to play anywhere else. Learned that pretty quick from my parents. And then went to graduate school at St. Louis University, and then followed that down to St. Jude, where I worked in a really world-renowned tumor biology laboratory. And then coming up here, the idea was, Jason, look, we want to do a lot of basic science to make discoveries that we can then translate into the clinic. And at the time, back in 2001, and I'm sure no one is aware of this, we had at WashU 5 oncologists. That's it. The Siteman had just been named. They only had 5 physicians working in oncology. And I was the first molecular oncologist working in the laboratory. Now we have over 150 oncologists, and we have over 125 basic scientists in the labs. So the amount of investment that WashU has made over 20 years is huge. And unfortunately, that's not because of the state of Missouri. All the money is federal NIH dollars. Okay, so WashU is, I think, number 4 or 5 in NIH dollars, 4. And, we're right up there with the Harvards and the MITs and the UPenns of the world. So to have that in your backyard is pretty darn impressive. And it's one of the reasons why we're able to attract such great scientists and such great physicians. And so, as sort of the 20th largest metropolitan area in the country, to have what is essentially was just ranked the #1 cancer center in the country, to have the #4 amount of dollars for medical research is pretty huge, and I'm really happy to be part of that. And it's continuing to grow. So my lab is really interested in sort of what makes a tumor cell a tumor cell. It's a very basic question, very fundamental. And back in the early 2000s, we did not know a lot about it, all right? We've sort of begun to pick it apart, almost like you would work on a car. So the best analogy that a lot of us use for a tumor cell is think of it like an automobile. But there are some twists to this, First, we want to know all the parts of the car, right? So we're pretty satisfied that we have a good understanding of what it takes to make a car, a tumor cell. And then we have to identify, what is it that takes you from a normal cell to a tumor cell? And over the last 15 years, we figured out, well, it's really the accumulation of lots and lots of mutations. Hundreds and oftentimes thousands of mutations. And they change sort of the properties of a car. They can turn it from for those of you like me, grew up in the 80s, Yugo, really slow Yugoslavian import car. And then a tumor cell wants to be a Ferrari. So it has to change how it looks. And that requires lots and lots of mutations. Now, lucky for us, these mutations are completely random, utterly random. There isn't a thing you can do to change what is about to be mutated. You can't do anything. But luckily, it's random. I often joke with my students that, man, if we were really unlucky, the tumor cell would know exactly what it wants, and it would mutate it. But it can't, all right? Tumor cells don't think. They just react and adapt. And so they randomly mutate their DNA until they get an advantage. It could be that, oh, now that you go, I've added a 5th gear. Now I don't have to go 35 on the highway. I can go 45 on the highway, right? And it's this accumulation of mutations or hits, as we call them, that takes you from normal to tumorigenic. Now, the students will all laugh. I always tell them this joke that ages me. It's an analogy. And raise your hand if you remember the commercial where the owl was sitting in the tree licking a Tootsie Roll Pop, and it said, and don't raise your hands because you had to Google it the first time I told you. How many licks does it take to get to the center of a Tootsie Roll Pop? And he goes, 1, 2, crunch, 3, right? So what we were all interested in on a grandiose level was how many mutations does it take to go from normal to tumor? Is it a set number? And work done in the early 2000s showed that it's 5. The magic number is 5. That's pretty scary, right? But remember, all those mutations are random. It has to be 5 perfect mutations to take it from a normal cell to a tumor cell. Lucky for us, most of our DNA is worthless, right? We have evolved to have worthless chunks of DNA in all of our cells. Thank God, because most of our mutations don't do anything. And in cancer, we call those mutations, I name them after my wife. They're the passengers in the car, okay? They literally do nothing but sit there and enjoy the ride, or that's what they should do. Sit there and enjoy the ride. Now, I'm a passenger with my wife from time to time, but it's very hard to be the passenger. But the mutations that occur in passengers don't do anything to the cells. And that's 99.999% of the mutations. It's only the ones that matter, that affect what the car is trying to do, that will give you normal to cancer. So where are those mutations? So what is the most important part of your car if you're the driver? The steering wheel? Tumor cells don't care about that. They'll go anywhere. The gas, there we go. The gas pedal, the accelerator, right? Those are the most important genes to a tumor cell. They want to go fast. Now, unlike a car, we don't just have one gas pedal for tumor cells. There are dozens of them. And they only need to screw up 5 of them, okay? They only have to screw up 5. There's dozens of them. But it has to occur randomly. So how can you sort of account for the randomness? And how do we tend to think of that in science? Because we can't watch it happen, right? I can't go to someone and go, hey, you know, I'd love to take a biopsy from your breast every week to see what your random mutations are doing. No one's going to sign up for that, right? So we're only going to see it at the beginning in a normal setting and at the end when there's already a tumor. We're going to miss the process, but we can study it in the laboratory. I like to think of the mutations that are going to happen no matter what we do as sort of buying mutation lottery tickets, except you don't want to win this lottery, okay? Now, how many tickets do you buy every day? Well, it depends on what you're doing. If you eat crappy food, buy a ticket. If you don't exercise, buy another ticket. If you smoke, buy a couple hundred tickets, right? If you're diabetic, buy a ticket. If you're out in the sun all day with no sunscreen, buy a few tickets. If you work at Chernobyl, buy a couple thousand tickets. Even just sitting here right now, every time our cell duplicates its DNA, it messes up a little bit. So no matter what, every day we're buying at least a ticket. Now, not all those tickets are going to be harmful, right? Because they're random. And we also have another advantage within our own DNA. So if something is broke, what do you do to it? You fix it. So we've got these great proteins in our cell, within our DNA, that are around to fix those mutations. Now, they can't fix all of them, but they're pretty good. They're pretty good at fixing them. And so what happens is, sorry, Steve, I got to stay in my corner over here. What happens is, as we get older, our repair people get worse. And so we begin to make more and more mistakes. And so all those lottery tickets over time, they tend to add up just because we're getting older. And that sort of is exactly what you see in the general population. If you look at the incidence of cancer, and it doesn't matter what state you're from, whether you're Democrat or Republican, it doesn't matter. You're always going to be exponential, meaning at a very young age, cancer is relatively rare, but at an old age, it's very, very prevalent, right? That's a brutal exponential curve, primarily because as we age, we cannot handle all those mutations. We can't fix them fast enough. So they begin to accumulate. And now your risk of losing the lottery is much, much higher. So some of those bad tickets are accelerators, gas pedals. What do you do if you don't want to go fast on the highway? Put on the brakes, okay? So the things that are the accelerators that make our cells go are called oncogenes. Those are the bad tickets that are going to get mutated, that are going to eventually cause cancer. The things that repair and the things that stop, so our mechanic and our brake pedal, those are tumor suppressors. And they're around to help us. But they can also be mutated just like oncogenes. And so that can also be one of those 5 hits. So what my lab works on is sort of the network or the interaction of all those gas pedals with all those brakes. And what is going wrong in cancer? What is the mutational burden that's making a normal cell look like a tumor cell? Now, we do a lot of this in breast cancer. Most of my lab probably has no idea why we work on breast cancer. This is very personal to me. I have a sister, 2 nieces, a wife, 2 daughters, and we lost a really good friend when she was 38 years old with breast cancer. Triple negative, the worst kind you can get. She had 3 kids at the time, and it was really hard. And there was not a lot of work going on the basic side. Even today, the number of treatments that are out there for the most aggressive forms of cancer, breast cancer in particular, we're still treating women the same way we were 30, 40, 50 years ago. Very few treatments have come into the clinic. Now, there are a couple that are really helping out. You probably see commercials on TV, right? You know, they have all these actors on there and they're like, I'm living with ER positive breast cancer. And so I take palbociclib. I don't even know what the fancy name of it is that the company gives them, but it's the new CDK4/6 inhibitors. We all know what they do. And you get that if you have estrogen receptor positive breast cancer. It prolongs your life, but you will still relapse. And so it's really just buying time. But we want to get better than that, right? We want to take it all the way, make this sort of a chronic disease where people actually go into remission long term and don't have to worry about it. And so for my lab, it's sort of figuring out what are the connections that are going on between those oncogenes, those accelerators, and the tumor suppressors that are the brakes. And so we model that in the laboratory. So we utilize animals, mice primarily. We utilize cells. We utilize tissue from patients. And we do it all the time, 24/7 in the laboratory, to try to get to the next step, and then the next step, and then the next step. So it's a slow process. They'll be the first to tell you it's slow, it's demanding, it's grueling, which I think is why they enjoy coming out to meet people and to partake in people who are not scientists, right? Whew, it's crazy. Because when all my wife's friends meet me, they're like, oh my God, your husband's a scientist? He does not look like a scientist. He does not act like a scientist. Like, I'm in the lab all day thinking about science. When I get out of the lab, I have to think about something else. Or I will end up driving all of them crazy with all my ideas. Right? I'm the type of guy, I have a pad of paper next to my bed because I will wake up with a crazy idea and I'll write it down. And I'll wake up in the morning and I'll come into the lab and I'm like, hey, I think we need to do this. And they're like, when did you think of that? I'm like, I don't know. It was like 2 a.m. I don't know. So it's constantly in our minds and thinking about it in ways that we can go from here to here in treating patients. So the types of people that come into the laboratory, that's the next biggest question I get. They're from all over the world, okay? Doesn't matter. They all have gone to college. Some get their PhD. I'm trying to convince one of my students that she just needs to get her PhD. So can we all just tell Jade, get your PhD? All right, they come from everywhere. The workforce is right now about 60-40 women to men. It's probably 60-40 international to US citizens. It's very hard to convince kids who are interested in science to go into research. Because what do most of them see and what do they want to be? A doctor, right? A doctor. I want to be a doctor. Nobody, name a show on NBC that's about scientists making discoveries. That is not a comedy. Right? I know, it's very hard to convince students to go on this long path. You graduate college and you go into graduate school as a PhD. Your compatriots are going out making 6 figures, and you're in graduate school making $30,000 a year, and you're working 24/7. You do that for 6 years, then you go do a postdoc for 4 or 5 years. Your pay goes up, you get like 45, but now your friends are making 200 and you're making $45,000, again, working 24/7. But then you get to have your own lab, but we're 10 years later, okay? It's a long road and it's very hard to convince students to do that. On the flip side, the ones that do, they're incredibly dedicated. And so, you know, you should really feel confident that when you see someone up in front of you talking, or you meet some of them, they're really in this to win this. They're certainly not here to make money. They're in it to figure it out. And to me, I get to see that every day. And it's constantly changing. I've had dozens upon dozens of people through my laboratory over the years, and it's always fun to see where they've gone and what they're doing now, and how they're now getting their own group to figure out their own discoveries and new treatments. And so it's sort of this growing entity that happens. And the more you get to interact with that, the more you'll sort of understand. We do a lot of work, again, trying to disseminate what it is we're doing in the laboratory so that you'll see what you're fighting for out in the public, what we're actually doing back in the laboratory. We've done a lot with the American Cancer Society. They were my first grant at WashU back in 2001. I got $30,000. It was enough to do like 3 experiments. And we were like, what do we do? Oh my God, they gave us the money. Alex, they gave us $30,000. What do we do? And you start thinking of, you know, big questions. How could we transform what we're doing? Not just take a step, but like, can we skip some steps? We tend to think of those sort of as our half-court shots, where we might have an idea based on some data that we have, but we want to make a huge conceptual leap. And we're like, let's do it. We're young. Let's try this. I think I was 30 years old at the time, and I'm really young. And we tried it, and it hit. And we've turned that one experiment for $30,000 into about $38 million in federal funding over the years. And thanks. A host of clinical trials, a lot of new ways of thinking of cancer. And now I think our work, we're really on the precipice of some big breakthroughs that are not just going to be for breast cancer, but now we're getting into lung cancer as well, because some of the connections between the brakes and the gas pedals are the same. The difficulty actually isn't on how cancer does it, because there are only so many ways that it can figure out the puzzle randomly. It's that everybody is different. You all have something different about you. And the way I like to think of this is something I learned early on, which is how I react to certain types of medications. So if you've got a really bad headache or ache, who takes Tylenol because that's the only thing that works? Okay, just a couple. Who takes Advil because it's the only thing that works? Who takes Aleve because it's the only thing that works, right? That's actually genetics working in the background about your sensitivity to NSAIDs and anti-inflammatories. And so the same thing is sort of compounded in cancer, that there are things that are that we might treat one patient and it works, but another patient, we give them the same treatment, they have the same tumor, but it doesn't work for them. And so we're starting to move into this era that we now call sort of personalized medicine. So previously, someone comes into the clinic, we have about 850 women with breast cancer that come through the clinic every year, and most of them are going to get standard chemotherapy. And it's going to work on around half of the women initially. About half of that half is eventually going to relapse. And the problem is we don't know who it's going to work for. And we don't know who it's not going to work for. Obviously, if we knew who wasn't going to respond, we wouldn't give them that treatment. We would try something else. And so now what we're trying to do is figure out why this sort of group of women responds and why this group doesn't, and treat them differently. So that's one of the things that's going on now. And it turns out that part of that is their genetics, but the other part is sort of how their networks are put together. One of the things that we've recently discovered in triple-negative breast cancer is that most of us probably aren't aware that triple-negative breast cancer is much more prevalent in African-American women than European descent women. Much higher, 2 to 3 times more likely to develop triple-negative breast cancer as an African-American than as a Caucasian. No one understands why that is, and it's much more aggressive, highly metastatic, very poor survival rate. We now sort of understand the connections that are being made in the cells that are sort of preferred in African-American women than in Caucasian women. So now we're beginning to understand, okay, how could we treat them differently in the clinic to get a better response? Okay, and so that takes a lot of people. It takes labs, it takes clinicians, oncologists, it takes radiologists, it takes radiation oncologists. Everybody has to work together. And that's one of the things that WashU does such a great job at, is bringing all these different people together to come up with new ideas and new treatments for women. The last thing that I want to get into about what we're doing is sort of how do we change the way we think about individuals in the clinic to make their outcomes not only better, but more personalized. And so we've sort of switched our modality in the laboratory from just working on cells or working in mice to sort of engineering people, if you will. Sort of coming up, the term that a lot of people use is avatars. So a woman comes into the clinic and she has a breast cancer diagnosis, and we take a biopsy of that. Part of that goes to pathology so that they can tell what's going on. And the rest of it, no one ever really does anything with. So we gladly take that. And we have now these devices. I have one in my pocket. I'm going to pass it around to you guys. So this is Jade designed this. This is why I'm telling her she's got to keep going. This is so amazing. And what it allows us to do is put a mammary gland on a chip. So if you hold it up to the light, you'll sort of see a design, if you will, that's embedded within this little piece of plastic here. And it allows us to actually put a woman's tumor cells into the device, other cells that are normally around it, so that we can mimic her in this. And you can imagine, what can you do with this? Well, if we had 100 of these, we could give 100 different treatments all at once within a few days and figure out how she's going to respond before we then give her the treatment. So the size of this is incredibly small. Again, WashU is one of the few places in the country where you can actually do stuff like this, manufacture this on your own. And it's pretty amazing to have this in our own backyard. So not only are we using this, but there are other labs now that have sort of latched onto this idea, and we're all working together to try to figure out the best way to sort of make this avatar on a chip so that we can treat it. The cool part about this is you can put these little, here's where I'm going to go off the rails, Jade, because I don't have my glasses. I'm 52, I don't have glasses now. Oh, man. So you can put these little tips in there, and we can load them with fluid, and now we can create interstitial flow, just like you would get in the body from a heartbeat or from your lymphatic system. So we can flow drugs through our mammary glands. We can flow other cells into the gland. We can do anything we want. And we can watch this all in a microscope because it's clear. We can watch it in real time, and we can do hundreds of these. So I'm just going to pass this around. You're not going to break it. There's nothing in it, right, Jade? You gave me a blank one, I hope. Okay, it's a blank one. And it costs us about $1 to make one of those. So the cost is much, much less, which is important because, you know, Missouri Cures does a lot to inform you. The American Cancer Society does a lot to raise money. The NIH has been like this since I've been a researcher. We haven't really changed at all, money-wise. And so we have to think of new ways to do more with the same. And so this is one of the things we think we can scale this so that we can make it cheaper. Mice are expensive. They don't talk back, but they're expensive. This is really inexpensive. And if we can sort of figure out what to do with women in the clinic when they come in on an individual basis, one, we'll know how not to treat them, and two, we'll know how to treat them. And that's really where we're heading. So I'm happy to answer any questions that you all might have. Feel free to shoot them at me. Yeah. Right. So the question was, can this strategy be utilized sort of in the new AI realm and in the realm of sort of accumulating large data sets? Absolutely, yes. I joke with the lab that, you know, they sequence something new every day, and now we're running out of stuff to sequence, right? But every woman who comes in to WashU and has their breast cancer analyzed radiologically, biopsied, they're getting sequenced, all right? Just because we need that information. So we have large data sets that have sort of our mutations. Now, we don't know So how many mutations does the average breast cancer patient have in one tumor cell? How many hits, how many mutations do you think it has? Just throw out a number. At least 5. You should give me a class. At least 5. Yes. At least 5. So higher than 5, less than. What do you think? Random mutations. 45-year-old woman buying a lottery ticket every day. What do you think her chances are? How many mutations does he have? 42, 300, much higher. Huh? 60,000. No, way too high. So 1,717. That's the average number of mutations in a breast cancer cell. Now, we only need 5 bad ones. So that means of those 1,717, at least 5 are bad. But it could also mean 1,712 don't do anything. So how do we know which ones are important? It's really hard. So big data gets us what I call a laundry list of crap. And we got to sift through it to find that nugget that we're looking for. That's really hard. And that's sort of the funnel right now that we're stuck at, is trying to analyze that much data. Now, dun, 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 to the rescue, AI, right? You know, Arnold Schwarzenegger comes in, says, you know, Terminator's going to figure all this out. AI is going to solve everything. AI has not been used on big data sets yet. Right now, you can use ChatGPT. We were messing around with it today in the lab. I was messing around writing a letter of recommendation for a medical student, and the ChatGPT actually wrote a better letter than I wrote. It's pretty crazy. You just put in like some of the things that you like about this person, and it writes you a whole letter. Now, the thing that it will do for science is a lot of the code that we use to sift through the data, it doesn't necessarily write it, but it will go through and find our mistakes. And so it's really good if you put in your code and you're like, look, I cannot get this to work, ChatGPT. What did I do wrong? It'll go, oh, you're missing this. And so it will get us there, but it's not there yet. Yeah, right? I'm still on the wait list for 4.0, by the way. You would think WashU would be really high. Yes. So everyone that comes through Barnes, so the question is, every woman who comes through Barnes with a breast cancer, are they automatically sort of entered into what my lab can get their hands on? It depends. Right now, everyone who's biopsied can or cannot sign the letter releasing their tumor to the university for research. 99.9% of them do, okay? By the time I get it, it's completely de-identified. I have no idea who it's through. All I have is a long number. But I do know everything about them. Aside from their name, I don't know their exact date of birth. I know how old they are. I know their zip code, because sometimes that's important information to have when looking at sort of incidence rates. And I know everything about them in their pathology of the tumor when it comes back from the pathologist. But you don't have to do that, but most opt to do that. You don't have to be on a clinical trial to have your tumor analyzed. I would say, I think our clinical trial rate right now in breast cancer is like 25.4% of patients in breast cancer. So 75% of the patients are getting standard of care. The other 25% have failed standard of care and are now on clinical trials. So some of it, yes. Absolutely. Absolutely. If we get mutations that we know are prognostic or theragnostic that tell them, oh, they should get this treatment, then absolutely that goes into the hands of the physician.
I know you're a breast cancer person, but are there any other types of cancer that are doing similar research?
So are there other cancers that are doing similar research to us? The answer is absolutely. If you name it, it's happening at WashU. Okay, so I would say that, in terms of just sheer numbers of patients, solid tumors are the ones that are sort of up there in numbers, breast, prostate, lung. Those are the big three. With those three alone, you're at 750,000 patients a year in the US. And then you have, your liquid tumors, leukemias and lymphomas, have a much higher survival rate, sort of different types of treatments. There are a lot of immunology treatments right now that are going on, but those are primarily being successful in what we call liquid tumors, primarily because the solid tumors, they're really hard to access, right? If talk to Jade, there's old data that now is becoming very pertinent, which, the question has always been, why did the drugs not seem to affect solid tumors, but do great with liquid tumors, even though the types of mutations are the same? Well, it turns out that the solid tumor has sort of this mechanical property of it, where it has a higher density, and it sort of flows out from the tumor because of that. So think of it as leaking outward. Whereas liquid tumors are just sort of in the milieu, and it's easy to treat them. So your drug is sort of swimming against the current, trying to get to a solid tumor. It has to sort of act like salmon. That's very hard to do. The treatments that are going on now are sort of these treatments that will activate your own immune system to fight the tumors. Some great stuff going on right now, a lot of it at WashU. But it's been very disappointing in solid tumors, primarily because you're asking B cells and T cells, I'll take it back to high school biology now, you're asking your immune system to swim upstream against the current to get to those solid tumors. And so it's been a hard battle. So even though everyone's working on everything, some are proving much more difficult than others.
One from a guest online asked, are you doing any research or have you looked into anything about how to decrease the number of lottery tickets? You mentioned things like smoking and diet. What other things can people do? Or have you seen people can do that?
It's behavior, folks. It is behavior. So obviously there are deleterious behaviors that can get you more tickets. Sitting out in the sun without any sunscreen, smoking, drinking. Alcohol is, even though it doesn't cause mutations, it's a modifier of them. So it's sort of a stimulant for tumor cells. And so even that is something you want to avoid at great quantities. Now we sort of also understand that those everyday tickets that you're buying, because you're just alive and your cells are always dividing and they're going to mess up from time to time, diet can actually reduce the amount of damage that is occurring from that everyday activity. So we just had a speaker come in town that talked a lot about the antioxidants and other sort of scavengers of bad things for your cells, doing sort of this whole food, non-animal diet. And there's a lot to be said for that. I think that's going to be sort of the next big thing. It makes me cringe because I love my animals. But it is having a huge effect in some of the preclinical trials that are going on. And so there are other ways to get your protein that don't bring along the same sort of buy extra lottery tickets that you would get from consuming meats. We had a speaker last week, and I left the talk. I was really excited for their work, but I left just hanging my head going, wow, this is really depressing, because it turns out that there's a sort of modification that occurs in your cells if you eat meat that was cooked on a grill. And I was like, really? You had to tell me that today? I chose to go to this talk. And so, we're learning more and more about what some of these drivers can be and how you can curtail that behavior to sort of limit the number of lottery tickets. But at the end of the day, again, it is still about, the unlucky accumulation of the right kinds of mutations. I give an example all the time to the students that I teach. My wife's grandmother just turned 94. She's up in Rockford, Illinois, and she goes to a doctor once a year religiously. She has smoked camels since she was 16. We got her down to 2 packs a day now, which is a good battle. We bring her Missouri cigarettes because they're cheaper than Illinois cigarettes. And she drinks a Schlitz beer every night before she goes to bed. I don't know. Oh, and every food that she cooks in her house is made with bacon grease. So she does not have a lot going for her health-wise. And every time she goes into her yearly checkup, and we might have a new doctor, and they go, well, Doris, I'm going to take a chest X-ray today. You're still smoking, and there's probably going to be something there. I'm like, there's not going to be anything there, I'm telling you. We've been doing this for 28 years. She's clean as a whistle. She looks like a 16-year-old on an X-ray. And she does. I don't know how that is possible, other than there's something about her genetics that makes her really lucky when it comes to her lottery tickets. Because believe me, she's buying thousands of them a day, and she still hasn't hit the lottery. So, I don't know. I don't know.
Standard of care still PAC mostly, and how far out are we from what we talked about with first blood?
So it really depends on what type of breast cancer you have. Oh, the question was, what are the current treatments in breast cancer, and how close are we to more personalized treatments? So right now, we sort of put people in 3 bins when they come in with breast cancer. If they're ER positive, they're going to get some type of estrogen inhibitor. So we're going to deprive them of estrogen to sort of starve off their tumor cells. Now, the standard of care with that is one of these CDK4/6 inhibitors, which you see on the commercials all the time. So that's now the gold standard. So there's a double treatment for ER positive women that replaces chemo from 40 years ago. If you're HER2 enriched or positive, you're going to get a different treatment than the ER positive. All right. So you're going to get a monoclonal antibody that prevents that receptor from working. It's called Herceptin. And there's a great movie. There's a great Harry Connick Jr. movie that talks about the guy who made the big push to utilize Herceptin on women with breast cancer. His name is Dennis Slayman out of UCLA. Awesome guy. I joke with him, we're on study section together at NIH. I joke with him, but how did you get Harry Connick Jr. to play you? I mean, that's everybody's dream, right? And because he doesn't look anything like Harry Connick Jr. And he goes, I don't know, that's just who signed the contract. And I'm like, nah, I think you probably said if you're going to make this, it's got to be Harry. But anyways, 40 years ago, HER2 positivity was a 0% survival until Dennis figured out that this antibody would work. It was made by a company called Genentech. The movie is all about his fight with them because they did not want to give him the drug to test on women with HER2 because the company had another drug coming out for arthritis. They were brand new. They did not want to tank their stock by having a trial where a bunch of, their quote, a bunch of women with cancer are going to die during the trial. And so they refused to let him have the drug. And so he went through the back door because he knew one of the chemists there, and he tried it anyways. And then he went to them with the data and said, can I now try this on these patients? And he was allowed to do 20 women. And they all did great. And now that's standard of care for HER2. Unfortunately for TNBC, they get standard chemotherapy, which is taxanes and cisplatin treatments, so platinum-based chemotherapy. So very, very toxic. It's the sort of abysmal story you always hear about with cancer patients, and that's a brutal treatment, but that's the only one we have right now. And that's 25,000 women a year. Yeah. Taxanes, there are a whole bunch of different taxanes that are out there now, but they're all terrible. Anybody else? Oh.
How does it point to that other cells know that, hey, we need to copy this gene and use that action?
No, that's a great, it's great. So it doesn't, luckily for us, it does not work that way. If it did, we would all have cancer. So the 5 hits have to happen in the same cell. Okay? The same cell has to get the 5 perfect hits. So for those of you that did math, it's like 5 factorial in order to get that. And it's completely random. So most of the time, when it gets 1 hit, that cell's not going to turn into anything. It has to get 4 more perfect hits. Now, it's going to get thousands more randomly, but it has to align the other 4 hits perfectly. If his neighbor gets 2 and he gets 3, they don't combine. So it has to happen in 1 cell. Yes, it does. Yeah. Right. So the question is, when these tumor cells metastasize, are they all surviving the journey, or are they all dying, or how does that work? Well, it turns out that a lot of work has been done in the last 10 years on this. Oh, man, I keep forgetting. And a lot of work's been done on this, and it turns out that it's a rough journey, right? Cells are getting out all the time, and we tend to think of that as, when the horse is leaving the barn. The problem for us as researchers and physicians is there's nothing that tells us when that has actually happened. The size of the primary tumor does not dictate when the horse has left the barn. So there's nothing right now that we can do to a patient to know whether they have metastasized already, unless we see very large metastatic lesions. And to see that, you need millions of cells to see that. So when they leave, it's very much sort of like the seed in the soil from the Bible. There are 4 locations where they can survive: the bone, the brain, the lung, and the liver. BBLL. That's all you got to remember. The only 4 metastatic sites that can handle tumor cells. Now, why do they survive there? They probably like it, right? It must provide them with something that they need. And I tell students all the time, why do we not develop a tumor? A breast cancer patient never comes in and says, and you go, oh my gosh, you have a huge tumor at the end of your fingertip. That must be a metastatic lesion. Well, I tell you what, I guarantee you there are tumor cells that make it down there. They're going through the whole circulatory system. I guarantee they make it down there because you have capillary beds there, but they don't survive. And so we don't know yet what the rules are that govern that. But it's a huge area of research, because take breast cancer, for instance. If you could prevent the horse from ever getting out of the barn, it would just be a chronic primary tumor that you would just deal with over time. It wouldn't be life-threatening. That's not the same for other types of cancers like brain, lung, liver, bone. But for breast, prostate, pancreatic, you could sort of deal with that. Yeah, in the back. Okay, so first question was, What was the first question again? Oh, risk of recurrence. If you've had cancer, why is your risk much higher? And it's twofold. The first is that we can never be sure that we got it all out in the first place. And more importantly, we can never know if there isn't a metastatic site that's just waiting to pop up. Like it's already there, it's just sitting there. It didn't die from the treatment, but now something in your life happens and it reactivates itself at that distant site. And now all of a sudden you have a recurrence. Okay, but most recurrences happen because at the primary site, we didn't get the whole thing out. Okay, the second part behind that is that your treatment is causing more genetic damage. Chemotherapies work because they screw up your DNA so much that the tumor cell is dividing so fast that it can't deal with it and it just dies. Your normal cells are getting damaged as well. So you're creating, by taking chemo, you're creating more lottery ticket chances. Like lots more. Classically at St. Jude, one of the things that we always worried about was, you know, with pediatric cases, a lot of the leukemias that come in, the most common variety, the survival now is like 98%. But the problem is 50% of these kids will develop a secondary tumor later in life. But then, you know, you go, well, gee, should we not treat them as harshly and just have less kids survive? Or do we worry about that secondary tumor later? And that's sort of the tack that people took, is survive now, deal with everything else later. And the same thing happens in adults.
I think we have to leave it there.
Thank you all very much. Appreciate it. I'll be around finishing my beverage if you have more questions. And whoever's got my device, hey, come on, unless you're going to pay for it. Oh, Jade already has it. Thanks.
Make it your. Well, I wanted to thank Dr. Weber one more time. Let's give him another round of applause. What a great presentation. I don't know about you, but I feel like I learned a lot. Once again, thank all of you for being here. Thank you for those of you who joined us virtually. We really appreciate it. And thank you to Second Shift for donating the space to us today and being so hospitable while we get everything set up and allowing us to be here tonight. And if you have questions for Dr. Weber and you're online, please shoot them to me. I'll be sure to send them his way. And thank you all. If you haven't gotten a beverage from Second Shift, please do and show your support. I'm sure they would appreciate it. Thank you and have a good night.